build Pascal's triangle. Now, when I say the C numbers, since I'm expanding to the fifth power, my coefficients will need to come from the fifth row of the triangle, or they would be 5C5, 5C4, 5C3, 5C2, 5C1, and 5C0. Now, for me personally, if I'm doing the entire expansion, it takes me a long time to type those into my calculator. So for me personally, it's faster just to build the triangle. And remember, when you build the triangle, you put a 1 on each end, and then you put numbers in between. So this would be 4, 6, 4, and then 1 and 1, and then in between, 5, 10, 10, 5. So those are the numbers that I need, that last row there. That's what you would get if you typed all these into your calculator. Those are the numbers you get. So we have a 1, 5, 10, 10, 5, 1. There are our coefficients. All right, what happens next? Stephen, you doing this? What happens next? What do we do now?
I usually take that on
I put in my variables. So for this particular problem, we have an x and a negative 2y. We have an x and a negative 2y. All right, now what? I put in my exponents, and we put in the exponents by starting with the first variable, which happens to be x, and in the first term of this problem, x will have an exponent of 5. And then we just go down. And then the y's do the same thing, right? But from the other end. Now I always put, especially when I'm all crowded like this, I always put plus signs to separate those terms. These are individual terms and they need to be simplified individually. So this term right here would be what? Just x to the fifth. Remember, anything to the 0 power is 1, so that's like not even there, x to the fifth. All right, what about this next term? You're multiplying all this together. Negative 10 x to the fourth y. This is where we start making mistakes. What's that one going to be? Positive 40 x cubed y squared. Why is it positive 40?
Because negative 2 squared is 4.
Because negative 2 squared is 4 times 10. 40 x to the third y squared. What's next? Oh no, that'll be minus 80 x squared y cubed. Next, 80 xy to the fourth. And on the end we have negative 32y to the fifth. All right, here we go. How many ways can 4 geometry, 3 algebra, 5 trig books be arranged on the circular shelf if the geometry must be together and the algebra are identical? Oh my gosh, there's a lot going on. Okay, so first of all, we got to talk about how many things are we arranging. Well, you got to pay attention to this.
3. No, that means 1.
If they are together, then these are functioning as
1.
1. So there's 1. and then you have 8 more, so that's a total of 9.
Circular stuff.
But they're arranged on a circular shell,
So you
so
go
it
down
would
1,
be
8,
8
that's it.
factorial. So we're starting with 8 factorial. I'll go through that logic one more time. These are tied together, so they're functioning like one thing. There's 8 other books, so that's a total of 9, but they're arranged in a circle, so it goes down to 8 factorial. Now, what else do you have to put in the problem? That's where you start, but now there's other stuff. What else do you have to put in there? You're gonna have to multiply this by 4 factorial. Why?
Because of geometry books.
Because those books, when you tied a string around them to keep them together, you could have done that 4 factorial ways. What else? Divide by 3 factorial, because why? The algebra books are identical. And what do we do with identical things? We divide by them factorial. Right? Okay. All right, so now we need to talk a little bit about the next concept. On the homework that, let's see, the homework that I assigned tonight will be due on Wednesday. Okay, so the homework that I assigned tonight will be due on Wednesday. On Wednesday, we will go over what was due today, which was section 9.4, and we'll go over what's due, what I'm assigning tonight, which is due Wednesday, which is 9.5. Here's what we did yesterday. You know this already. We took a set of numbers like this. By the way, what kind of set of numbers is that?
Arithmetic.
Arithmetic. We know it's arithmetic because we're getting from term to term by adding, right? So we took this set of numbers and we said, okay, for whatever reason, I want to know the 502nd term. I don't know why, I just need to know that. So the notation would be A sub 502, that's the 502nd term. And we had a formula for that, remember? What was, does anybody remember the formula?
First term plus.
So in general,
The common difference.
the first term plus common difference times and minus 1. And in this formula, this is the first term. This is the common difference, which is the number that we add, right? And n is whatever term it is you're looking for. So for us, n is 502. So we will say what? 1 plus 3 times 501. So the answer to the question is
1504.
1504.
Good call.
That's what we learned yesterday. Okay? Now, I want you to look, I want you to think about this question.
He was giving it to me.
Harry deposits 3 cents in his bank, his piggy bank, on the first day
You got 3 cents?
of, let's say, on the first day of May. He deposits 8 cents on the second day, and 13 cents on the third day. If he continues this, here are the 2 questions. How much will he deposit on the last day of the month? And how much? It's really not deposited.
Lakes do so much value. So that's like A30.
Okay, so here's the situation, and there are the two questions. Are they the same question?
No.
What's different about them? This one is just asking me how much he puts in the bank on that particular day. But this one says how much total is in the bank, right?
Yeah.
Okay. Can I do the top one?
Probably. Yeah.
Yes, because the top one is just like what I just did. The sequence, it's really getting annoying. And I am so pumped up for the field trip. And I'm starting to even get like grouchy. And I shouldn't be. I should be elated because
Cut
the
him off the
field
field
trip is
trip.
in
Cut
sight.
him off the field trip.
All right. The sequence is 3, 8, 13, and so on. What kind of sequence is that? Arithmetic. So it's exactly what we just did. Which term would we be looking for? We're doing question number 1. Which
30th.
term?
31.
31st, so 31 days in May. So the first one is 3. What's my common difference? 5. N minus 1 would be 30. So he puts in 153 cents or $1.53 on the last day. Everybody okay with that?
That's crazy.
Now, how in the world, well, think about this set of numbers. You got 31 of these numbers, and the last one's 153. How in the world are we going to add those up? We do not want to sit there and, you know, put all those numbers in. We could. That would work, absolutely. You could add them up physically one at a time, but that's going to take forever. So what could we do instead? Well, you're not going to believe this. I'm going to erase the problem. We got it, right? So we know what we're doing. I got a little story for you. Doesn't involve me. It involves a little boy a couple hundred years ago. It was a Friday afternoon. Only little boys in the class, of course. I think he was in 3rd grade, 2nd or 3rd grade, something around there. And the teacher says, it's in France, the teacher says, okay, kids, they were driving him crazy. He says, okay, you guys, I want you to add up all the natural numbers from 1 to 100. You may have heard this story before, especially if you had Mr. Thompson. He tells it all the time. There we are, adding up the numbers from 1 to 100. Now, the kids are driving him crazy. It's a Friday afternoon. He is thinking, these are little children, he's thinking, what are they going to do? They're going to sit down with their papers and their pencils, and they're going to add 1 and 2. And then they're going to add in the 3, and then they're going to add in 4. And this is an easy exercise, but it's time consuming, right? So this is going to occupy their time, keep them quiet till the school day's over. Well, the teacher gave the instructions. Okay, boys, here's what I want you to do. He went over and sat down at his desk. This is a true story. And the teacher no more than got sat down at his desk, and up came this little boy with the answer. And here's how he had done it. Remember, it's like 3rd grade. He said, teacher, this is what you want me to add up. You want me to find this sum of numbers. But I know that addition is commutative. So I could add up this same set of numbers in a different order. And it would be exactly the same sum. If I were to add these two together vertically, so I had 2 of these sums, add them together, so 2 of these sums, each of the little terms, when I add, will be 101. There will be how many 101s? No, there'll be 100 of them. There'll be 100 101s. But 100 of the 101s is 2 sums. So 1 sum would be 50 101s. And so the answer is 50-50. Now, how does that problem apply to our dilemma? we want to add up this set of numbers. Can we use what he did, Carl Friedrich Gauss, one of the greatest algebraists of all time, could we use what he did to solve our problem? Well, was his sequence, this was his original sequence, arithmetic? Is this arithmetic? Okay, so let's analyze what he did. He said, I have to add up 100 terms. I'm going to use S to indicate I'm going to add up 100 terms. Where did that 50 come from? In his problem, where did that 50 come from? The total number divided by 2. So he had 100 over 2. Where did the 101 come from? The sum of what? What special sum? The first term plus the last term. So in a general formula type thing, the sum of n terms would be what? N divided by 2 times the first term plus the last term. Thank you so much. You just want me to, oh, yeah. Thank you. Okay. So n over 2, first term plus last term. There's your formula. If you want to add up the terms of an arithmetic series, when we add them, we call it a series, not a sequence. This is a series. If you want to add up the terms of an arithmetic series, this is your formula. How are you going to keep these two formulas straight? Because they both involve arithmetic. What does this one do for you? Finds the term. So if you're interested in a number in the list, just a single number in the list, this is your formula. If you want to add them up, this is your formula. So let's go back to Harry's problem. We want to add up the terms of this series right here. How many are we adding up? Go back to Harry's problem, number 2. 31. We're adding up 31 terms. We're at the end of the month. How much do you deposit in May? So our formula would say 31 over 2. 3 plus 153. Now remember, when you're putting in the formula, don't put the decimal point in there. This is 153 cents. 3 cents and 153 cents. And that, work that out, it's 156 times 31 halves. What is that?
There's a lot of math.
Well, certainly somebody's got a calculator. What is it?
Oh, I'm just doing it. 24.
25. There we go. That's how much you would have deposited. Now, I don't have any cool stories to go with it, but there is a formula that will also add up the terms of a geometric series. So let's review, first of all, what's our formula for a geometric sequence? What's the formula for geometric? Perfect. Yep, that's it. That's your formula for a geometric sequence. So if you have a geometric set of numbers, like 2, 10, 50, 250, if you have a geometric set of numbers, how do I know that's geometric? I'm going from term to term by multiplying. If you wanted to know what the 15th term in this list is, you would use this formula. But what if I wanted to add these up? Well, then I'd need a different formula, and here it is. That is the formula that will add up the terms of a geometric series. So if I were looking at this formula, or this series, I mean, and I said, let's add up the first 10 terms. Let's add them up, the first 10 terms. What would that look like?
2
2.
minus 2.
Yep.
Minus 2 times 5 to the job.
1 minus 2.
Can I put -4 down there? How did I get -4 in my denominator?
1 minus
1 minus
5.
r. Now, when I type this in on my calculator, I can type it in exactly as I wrote it, but I have to hit equals at the end of the numerator. So when I type it in, 2 minus 2 times 5 to the 10th, and then equals divided by -4. So the answer you should get should be 4882812. That is a huge number, kids. That's 4 million. Does that make sense to you that that number would be so big?
Yeah.
Yeah, because what did we talk about yesterday? Geometric sequences grow really fast. So if we're going to add up the terms, that's going to be a big number. If you were trying to simplify, would you be able to multiply the 2 and the 5? No. No. Just type it in exactly like I wrote it. Just make sure you hit equals at this point, and then divide it by. Okay? All right, we got a couple more things to talk about. So you need to take just a few more notes here. By the way, you now should have 4 formulas in your list. We have 1 more to get. Gonna work on it right now. Let's take the sequence.
I just asked them last week.
Okay, and I'd like you, since we're doing the sums today, let's add up the first 20 terms of this sequence. Would you just do that on your own? We're going to add them now. It's a sum. So I've given you 2 sum formulas. You got this one right here, and you've got this one. These are your 2 sum formulas. Which one are you going to use in this particular problem? The second one. And how do you know you're using the second one? Because it's a geometric sequence. What's your ratio? 1/2. All right, here you go. Go ahead. Use your geometric formula. And do that while I take attendance. Melanie's not here.
Yeah, I do.
Watching the height today too. I mean, she didn't do this.
Heidi's not here. Habecker's not here.
If I can find why am I going down to Oh,
Natalie, I saw your parents last night.
Sexiest thing I've ever seen. I don't know. It looks
Oh, she's on retreat.
What's with the one?
Okay. Did you get an answer? What'd you get?
20.
19.98?
Wait, no.
So 9804 something? Okay. Would you add up 40 of them for me? Now, the nice thing is, you're not going to change a thing except the sex code, right?
It's the same problem. You're just putting 40 in for it.
Yep, that's right, you're doing the same problem. There's a reason. I'm not just having you do this because it's fun. There's a reason.
I thought you saw
What happened? My calculator says 20. Is that what yours says? Add up 60 of them, quickly, add up 60 of them.
No.
You got 30,
Yeah, we did something wrong.
you did.
We'll get back with you.
Okay, type in these numbers, 20, or excuse me, not 20, 10 minus 10 times 0.5 raised to the 40th, well, or 60th, I'll do 60 this time, equals divided by 0.5. Shoot, I got 20 again. You guys, this doesn't make sense. Think about it. When we added up 40, so extend your list, when you added up 40 of them, you got 20. How can you add in 20 more terms and still get 20 as the answer? Can anybody explain that to me?
They cancel each other at the.
What's happening, kids, is this. You are saying 10 minus 10 times 0.5, or 1/2, to a higher and higher power. What happens when you raise 1/2 to a higher and higher power?
It gets really small.
It gets so small. And eventually, it gets so small that your calculator thinks of it as 0. So then, it thinks of this as 0. Multiplying by 10, that's still 0, right? So what is it left with? 10 divided by 1/2, which is 20. Are either one of these actually 20? No. This one is 19.9999999, and this one is 19.999 with even more nines. Neither one of them are actually 20. The calculator's just rounding them off. What you have just discovered is how infinite geometric series are handled. You can actually add an infinite number of terms. That's kind of mind-boggling. But you can add an infinite number of terms with this formula. This is how you add an infinite number of terms. Notice there's no end because it's infinite. But there's a key to it. How come this worked out this way? Because this got smaller and smaller and smaller. And the only way it will get smaller and smaller and smaller is if what about its ratio?
If it's a fraction.
Not just a fraction, but a fraction less than 1. So this will only work if your ratio has an absolute value less than 1. We'll talk more about that next Wednesday, but there are a couple of those in there. Okay.
You got really cool.
Yeah. I feel like I should slip this across a pond. It's like a pebble, I love skipping rocks.
Pebble skipping. You know what I feel like loves pebble skipping?
Okay, John, did you turn us off?
Yeah. I really want to go slip on rocks.